Okay, so you have learned in the first two sections in chapter 7 quite a bit about differential equations. You understand what a differential equation is. You're able to understand a direction field for a differential equation, what it means. You also understand now the Euler's method. The Euler's method to help you find, to get approximate solutions, approximate values to solutions of a differential equation. So those are very good things. But of course, ultimately, we'd like to, just like in any kind of equation, we'd like to be able to solve the differential equation. So let me give you a moment to copy down this example, okay, and then we will go over this very nice little example here. Okay, so what we have here is an initial value problem, because in this problem we have a differential equation, and accompanied with the differential equation is an initial value. So we call this type of differential equation an initial value problem. And because we have an initial value, in the end, we're going to end up getting a unique solution to this differential equation. Now, how do we solve this differential equation? Well, we're calling this a separable differential equation. And remember, y prime equals x squared over y squared. That can be written as dy dx equals x squared over y squared. Right? And for our purposes, it will be helpful to write the derivative of y prime as dy dx. So how many variables are involved? How many variables are involved in this equation, dy dx equals x squared over y squared? How many variables are there? Well, Ange says, let me ask you this. What's one of the variables? Okay, yeah, 2. That's right. That's right. Good, Javier. Good, Ange. Good, D'Angelo. 2 variables, okay? X and Y. That's right. Now, what's the independent variable in this case? Is it X or is it Y? Since we're taking the derivative of Y with respect to X, are we treating X as the independent variable or the dependent variable? That's right, Ange. X we're treating as the independent variable. And what we want to know, Y is some function of X. The question is, what is that? What is the solution to this initial value problem? Okay, so let's go to the next page and examine the solution. Let's go to the next page here. what we're going to do is we're going to separate the variables. We're going to separate the variables. Okay, and so again, I write y prime equals x squared over y squared as dy dx equals x squared over y squared. And what I'm going to do is I'm going to try to get the y variable terms on one side of the equation and the x variable terms on the other side of the equation. So let's say that I want the y variable terms on the left side of the equation. Well, I have here, okay, I have here a y squared. So I'm going to multiply through y squared on both sides of the equation. This means, hold on here. This means then, and maybe I can do it in kind of a light color, the y squared terms cancel out here, and then you're left with y squared times dy dx equals x squared. But now what I'm going to do is I'm going to multiply both sides of the differential equation by the differential dx. And so this means then, well, now the differential dx, okay, what's going to happen, right, is you're going to have simplification. And so you're going to end up with y squared dy. This is a dx, right? You're going to have y squared dy equals x squared dx right there. Okay, so this is all in the recording, but let me just kind of, sometimes I like to re-put things back in. Okay, so here at this step, the variables are separated. The variables are separated. And remember what we want to do. We want to find out what is y equal to. So, well, what if I were to integrate both sides of that differential equation? So, of course, if I integrate the left side of the differential equation, okay, and maybe I'll circle this. If I integrate the left side of the differential equation, then I have to integrate the right side of the differential equation. Seems fair, right? And the antiderivative of y squared, well, this integral here, the integral of y squared dy, that's an indefinite integral. So the antiderivative is going to be y cubed over 3 plus c1, some constant of integration. Similarly, on the right-hand side, the antiderivative of x squared is going to be x cubed over 3 plus c2, another constant of integration, and it could be the same or it could be a different constant of integration. This is why we use c1 and c2, because those constants of integration are not connected to each other. But to make our lives easy, what we can do is we can bring over the c1 from the left side over here to the right side. And so y cubed over 3 will equal x cubed over 3 plus c2 minus c1. And I'll call c2 minus c1, I'll call that c3. Okay. So at this step here, if if like going from here, if you had y cubed over 3 equals x cubed over 3 plus some constant, okay, that would be okay. You don't have to have like this step here, I added a constant of integration to each side, but then in the end, I ended up with a equation that just has a constant on the right side. So you could go from this step here to this step. That's fine without loss of generality. But, I'll call it like C3 because you see, every time I alter the constant, I have to rename the constant. So it's good to just, C1, C2, C3, C4, so forth. Okay, are there any questions? Are there any questions so far?
I have a question.
Sure, D'Angelo.
So you just put C2 and C1 to label your constants, right?
I'm sorry, C2 and C1.
Yeah,
Say again?
yeah, you just put the subscript C1 and C2 to label your subscripts. I mean to label your constants.
Right. Those C1 is one constant of integration. C2 is another constant
And
of
you
integration.
and when you subtract it in the bottom, you're not getting rid of it. You're just turning it into one constant.
That's right. I'm gonna call this C1 C2 minus C1. I'm gonna rename it as C3.
Okay.
That's right. Okay. Okay. Well, now we need to solve for y. We need to solve for y. So this looks like an easy equation. All right, no problem. So we have y cubed over 3 equals x cubed over 3 plus c3. And what I'll do here is both sides. Let me see here if I can make an adjustment. Yeah, all right, that's nice. I learned how to do that, but then it does that. I'll multiply both sides of this equation by 3. So then I have y, and naturally on the right-hand side, I'm going to distribute the 3 to both of those terms there. And so that's going to give me y cubed equals x cubed plus 3 times c3. But now I know that 3 times c3, I could call it c4, but I sort of know that, hey, I'm not going to need to do anything else. That's going to be like the final constant that I'm going to have. So I'll just call it big K. Now I just choose to call it big K. You could call it big C, something like that. Because now I'm ready to solve for y. Well, okay, so if I raise both sides of this equation to the third power, I'm going to get y equals the cube root of x cubed plus k. That's now a family of solutions. Okay, so remember, a differential equation, if we don't specify an initial value, and we did specify an initial value, but we haven't plugged it in yet. Right now, we're just solving the differential equation, and this is going to give us a family of solutions. Are there any questions so far? Okay. Okay. Well, then now we're going to apply that initial condition. Okay, one moment. Okay, sorry for the interruption. I have a landline at the house, and I'm just gonna have to learn how to turn that off. You know, I didn't answer the phone. I just put the phone in another room. All right, so here's the initial condition, y of 0 equals 2. And okay, so we're gonna substitute in for y, we're gonna substitute in 2. And for x, we're gonna substitute in 0. So 2 will equal the cube root of 0 cubed plus k, which means 2 equals the cube root of k, so k is 8. K is 8. So now we have a solution to our initial value problem. We've actually solved our differential equation. We have an explicit solution, y equals the cube root of x cubed plus 8. That's the answer. How many think that's pretty kind of cool? This separation of variables technique. Okay, Anne's just liking it. Javier's liking it. Okay, good, good. D'Angelo likes it. Okay. Okay. All right. So this example that I'm doing with you is actually example in section 7.3. It's example 1. And what I'd like to do is I'd like to go into the ebook and show you a figure that goes with this particular problem. It's example 1. So let me, one moment. The ebook here. Okay, let me bring that up here. Are there any questions so far? Okay. Okay. So this is the example 1 that we just did. Okay, and the figure, so that the general solution, as you recall, is y equals the cube root of x cubed plus k. So if we were to look at a plot, a picture of this family of solutions, there it is. There it is in figure 1. Now, the red graph, the red solution curve, passes through the point. Well, what point does it pass through? I mean, there's a lot of points on that, an infinite number of points on that red solution curve. But what very important point does that solution pass through? That's right, Taj. It passes through 0 and 2. So you see, the unique solution that we got, y equals the cube root of x cubed plus 8, that graph of that is that red solution curve. That's the solution out of the entire family that satisfies, that's the solution. The red solution curve is the solution to the differential equation out of the entire family of solutions. That solution satisfies our initial condition, that when x is 0, y equals 2. Okay, are there any questions on that? Okay, let me do another one with you then. Maybe this one I will try to do in the whiteboard. This actually is the third example from section 6.2, but maybe let me try to work it here. So here's an example. Solve this differential equation. Y prime equals x squared times y. Okay. So first, I'm going to write y prime as dy dx. So dy dx will equal x squared over y. And we want to separate the variables. Traditionally, I like to have my y variable on the left side of the equation. So that means I don't want it on the right side. So I'm going to multiply by 1 over y. And when I do have that, I'll have 1 over y dy dx equals x squared. Okay, and so, well, what are we going to multiply now on both sides of the equation? That's right. Good, Tosh. We're going to, good, Ange. Good, D'Angelo. We're going to multiply by dx. And doing so is then going to give us 1 over y dy equals x squared dx. We've separated the variables. Again, this is example 3 from section 7.3. What do we do now? Now that we've separated the variables, what's the next step? Integrate. Good. Good, Javier. Good, D'Angelo. We'll integrate both sides. Both sides of the equation. What's the antiderivative of 1 over y? Good. Good. ln of the absolute value of y. And that will equal, well, the antiderivative of x squared is x cubed over 3. And now we'll just add in a constant. We'll add in a constant. And perhaps I'll call that constant like C1. Are there any questions so far? All right. Well, I want to get the y. I don't want the log of y. I want the y. So what do we have to do to both sides? I know you've seen it before. Think for a moment. Exponentiate. Good. So, all right, I'm going to exponentiate both sides. There. Okay, and so now we have the absolute value of y equals e to x cubed over 3 power plus c1. But that means the absolute value of y equals, we could write it as e to the c1 power times e to the x cubed over 3 power. And e to the c1 I'll call c2. So the absolute value of y is equal to c2 times e to the power x cubed over 3. Are there any questions so far? All right. Well, we need to solve for y. We need to solve for y, not the absolute value of y. So what we're going to do is, if we remove the absolute values, then on the right-hand side we have to have a plus or minus c2 times e to the x cubed over 3 power. Okay, so this is no different than like, and I want to, be a little careful on my pages here, but like if I just maybe go over here where I have a little space. Let's go over here. Like if you have the absolute value, let's just say the absolute value of A equals 2. If the absolute value of A equals 2, what's A going to equal? If the absolute value of A equals 2, A is going to equal, what could A equal? Either 2 or negative 2, so plus or minus 2. See? And if you had the absolute value of an apple equal to 2, the apple would also equal plus or minus 2. You see? I want to say this the right way. Let me say it. Let me do a little bit better with that. Hold on. I mean, this is fine, but let me do this a little bit differently. Hold on. Okay, let's talk about y. Okay, let's talk about the variable y. But this is this is just a little discussion. If you had the absolute value of y equal to 2, y would equal plus or minus 2, right? If you had the absolute value of y equal to an apple, what would y equal? If the absolute value of y is equal to an apple, y would have to equal what? So if the absolute value of y equals 2, y could be plus or minus 2. This, what I'm doing here is not connected to the y in the problem. I'm just trying, but I want to talk about why this is true. So the absolute value of y equals 2, y is plus or minus 2, right? Y could be plus or minus 2. If the absolute value of y were equal to an apple, y could be equal to, that's right, good Taj, good D'Angelo, plus or minus the apple. So that's what we have here. This here on the right-hand side, this is like an apple. So when I remove the absolute values, y is plus or minus the apple. And that's how you get to this stage. But what we can do, see, is we can say, well, y equals then, we could write this as plus or minus C2 times e to the x cubed over 3 power. And then we can call C2, that plus or minus C2, we could call that A. So y, this differential equation, the solution in the end, okay, let me give myself a little space here. Now they might do it a little differently in example 3, but in the end, well, I'll go to the book now. Y equals A times E cubed y equals A times e to the power e cubed over 3. Are there any? I'll go to the book, but I want to make sure everybody's comfortable with this before I go to the book. So the plus or minus 2 times e cubed over 3 is the same as plus or minus c2 times e cubed over 3. That's why, you know, these two are the same. And plus or minus c2, well, that's just going to be a constant itself, so we'll call it A. Okay, are there any questions? All right, well then let me go ahead here, back into the book here. So looking, we just did example 3. We just did example 3. Okay, and y equals A times e to the x cubed over e to the power x cubed over 3. Okay, and so that's really, I mean, we're going to be continuing section 7.3 on Tuesday's class, next Tuesday's class, and we'll be getting into a 7.4 as well. But this is now, you know, separable differential equations are very important. There are a lot of famous differential equations that can be separated. Okay, and you know, yeah. Are there, and we'll look at some applications on next in Tuesday's class. Are there any questions before I stop the recording? Who's feeling good? Maybe give me a few thumbs up if you're feeling good with so far with section 7.3. All right, Javier, Jan, D'Angelo, Ange, Dodge, wonderful, wonderful. Hold on, some others too. Let's see here. David and Taj, wonderful. Okay, okay. Well, on that note, I will stop the recording.